I would like to make a comment on the fact that up to now we have been discussing gases or systems composed of molecules, consider only mainly the kinetic part of the energy. Okay, indeed, particles have internal degrees of freedom, and this will contribute to the thermodynamics, will contribute to the statistical properties. So these internal degrees of freedom can be, for example, if you have a monoatomic gas, you will have the electronic states, in the sense that your atoms will be composed of nuclei and electrons. And these electrons will be in a given quantum state. There will be even degrees of freedom which come from the nuclear state. Okay, so in particular the spin of the nucleus. If you have a molecule composed of, say, 2 or more atoms, then there will be vibrational degrees of freedom between the molecules. And also there will be rotational degrees of freedom. Now, and maybe more, but so how does one treat these additional degrees of freedom? Well, the idea is that generally the Hamiltonian will be a sum, so will be, say, the Hamiltonian of the kinetic part plus the Hamiltonian of the electrons plus the Hamiltonian which depends on the nuclear spin, etc., etc. Okay, and you can consider cases where each of these term of the Hamiltonian depends on different degrees of freedom or on different quantum numbers. Okay, in particular, we consider the case where all these the Hamiltonian can be diagonalized, and the quantum numbers specify the state of each of these terms. Okay, so if this is the case, when you compute the partition function, say the canonical partition function, then what you have to do is a sum over all the states of e to the minus beta times the energy of that state. So this sum means that you have to sum over all quantum numbers. Okay, and these are the eigenstate of this Hamiltonian, which is written as a sum. Okay, so it means that the eigenstates will be a sum of the eigenstate of each of these Hamiltonian, and essentially what happens is that this S, the state will be the state of the kinetic part, the state of the electronic part, etc., etc. So what you can do is to factorize this sum over the different contributions. Okay, and you can compute essentially independently each of these contributions. and you see that then the Helmholtz free energy will be a sum, which is the log of this, will be a sum of all these different contributions. And so you can deal essentially independently with all of these with all of these effects separately. Okay. And so of course, so for example, if you compute the specific heat will have a part which comes from the kinetic part plus a part which comes from the electronic part, etc., etc. So, and so at a particular temperature, some of these system can be considered to be as being in the ground state, so the corresponding contribution will be 0 because there is just one term which contributes to the sum. Okay, so for example, if you consider the electronic degrees of freedom, you have, say, for example, a simple atom like helium, and then there are the electrons. Now, you can consider different ionization state of the electron, where you remove one electron, and but the energies which are involved, the ionization energy corresponds to a temperature which is 10 to the 4 or 10 to the 5. Okay, so the corresponding contribution in the specific heat or in the other thermodynamic quantity from these internal degrees of freedom will only be important at temperature of order 10 to the 4 or 10 to the 5 Kelvin. Okay. So for this reason, for this reason, for example, if you have a gas of molecules like hydrogen, for example, then the vibrational degrees of freedom would be described at the first approximation by a gas of harmonic oscillators with a frequency which is given by the characteristic frequency of vibrations in the hydrogen atom. And so the treatment we have been doing can be of a gas, a system of harmonic oscillator can be used to describe the vibrational state of the system. Okay. Okay, so what I want to do today and tomorrow is to instead discuss a little bit more, no, today and Friday, is to discuss ideal quantum gases in some more detail. And in particular, I want to discuss what are the peculiar new phenomena which arise in the quantum regime. So I remind you that so these so the classical regime is valid when it's valid either when the density is very large or when the temperature is either when the density is very small or when the temperature is very large, where this lambda is the thermal wavelength, which is essentially proportional to T to the minus 3/2, but is h bar divided by 2 pi mk. So the 1/2. So this wavelength goes 1 over the square root of T, so that this condition is satisfied either when you have high temperature or low density. Okay. Now we are going to consider instead the case where this condition is not satisfied, and we are going to see what type of new physics arise in this limit. Okay. And so this, yeah. Sorry? Lambda to the minus 3?
No, n times lambda raised to 2 over 3 has to be much more than the
So this is a length, right?
Yeah.
So this is n divided by v times lambda to 3. So instead so you have an elementary cube, which is given by the thermal wavelength.
We go to 1 over t cube, I think. When
no, maybe I'm not understanding what is the question.
when we say for ideal cases, okay, we got the relation which is n over v over t cubed. The temperature raised to 3.
T cube, no, it's t to the 3 half. No, so this is the combination of which arises essentially everywhere. But we are going to see that this is the relevant parameter anyhow. So okay, so this parameter is essentially you have an elementary cube which is given by well, this is if you want the wavelength of a particle which has a kinetic energy kT and of order kT, and so you are looking at how many particles in your gas are in a volume of this given by this length. Okay, so in order to discuss this thing, we have to distinguish between the Bose system and the Fermi system. Yes, please. Okay, so 2 pi is up and not down. Well, it's in the book. Okay, so. But I think it's down. But okay. Let's discuss the ideal Bose gas. Okay. So for the ideal Bose gas, what we have to do is to compute the grand canonical partition function, which is PV over kT, and this is equal to minus the log of the sum of all the energy levels of E of is the sum over epsilon of the log of 1 minus z e to the minus beta times the energy. This is a sum over all the energy levels, and this z is the fugacity. case is the beta mu. And we are using the grand canonical. We are using the grand canonical ensemble. Now it is convenient to transform this sum over energy levels into an integral over energies. Okay, and in order to do this, what one needs to compute is the energy density. So how many energy levels are there between energy E and E plus dE? Okay, and so this energy density we have computed already a couple of times. So the number of energy levels which are between energy E epsilon and epsilon plus d epsilon is 2 pi v over h cube times 2m to the 3 over 2. So this is for an ideal gas. Okay, so the way you compute this is again by considering that the eigenstates are plane waves. Plane waves in a volume V have discretized momenta, which are k is 2 pi n divided by L, and then in this way you compute. And then the other thing here I've changed. Instead of expressing this in terms of K and dk, I've expressed it directly in terms of the energy. Okay, but it's a simple transformation. Okay. Now, one idea is that then you take this thing and you write it as minus. You substitute this sum with an integral. And the energies, of course, go from 0. This energy is, I remind you, is just the kinetic energy of the particles. So the energy is clearly positive. Okay? So the energy will go from 0 to infinity of A of epsilon d epsilon times the log 1 minus z e to the minus beta epsilon. Okay. Now, there is one problem when I do this, which is the fact that in this sum, there is also the contribution from the state with energy equal to 0. Okay, which corresponds to momenta equal to 0, to k equal to 0. Now, this you see, the density of state at energy 0 is equal to 0. So the contribution from this state does not appear here. Okay, so it's given energy 0. So what I should do is to, if I want to be precise, is to add explicitly to this term the contribution of the 0 energy state, which is just log of 1 minus z. So we will see that this is important. Okay. Okay, so this comes from the state epsilon equal to 0. Okay. Now, if I use this formula here, I write the equation for the grand canonical potential as minus 2 pi v 2m 3/2 over h cube times the integral from 0 to infinity d epsilon, epsilon to the 1/2, epsilon 1/2 log 1 minus z e to the minus beta epsilon minus log of 1 minus z. So you see this term, while this term is of order v, so is extensive, this other term is not extensive. Okay? So in general, will not contribute much to this, to the grand canonical potential. However, we'll see that it is important that we keep it. In particular, if you compute the number of particles, we know that is equal to the fugacity times the derivative with respect to the fugacity of this equation. And if you do that, this is 2 pi v 2m 3/2 h cube. And here you get the epsilon to the 1/2 times z to the minus 1 e to the minus e to the beta epsilon minus plus z divided 1 minus z. So you see you have two terms. One term is given by this. So you see here you have a term which is 1 over z to the minus 1 e to the beta epsilon minus 1. This is the occupation number of the state with energy epsilon. Okay, and I'm integrating this. So this is really the sum over epsilon positive of the expected number of particles in the state epsilon. And instead, this other term is the number of particles in the energy level with energy 0. Okay? So this I will call it as n number of particles in the positive energy levels. And now there is one. It is very practical to change variables in this integral to the variable beta epsilon, so called beta epsilon equal to x. And then if you do this, you can write this integral here as minus 1 over lambda cube times, well, let me write it as g. Okay. So let me do this derivation. So here, what you have to do, as we did last time, it is convenient to do an integration by parts. So if you take this, let me just take this integral here. So if you change variables to x equal to beta epsilon, then this is kt to the 3 over 2, right? Times the integral from 0 to infinity dx, x to the 1/2 log of 1 minus z e to the minus x. Now I do an integration by parts. So I integrate this guy and differentiate this. So this is the integral of this is 2/3 x to the 3 over 2, right? Times log of 1 minus z e to the minus x. And then I have the other term, which is 2/3 the integral from 0 to infinity dx 2/3 x to the 3/2. And the derivative of this. So the derivative of this is 1 minus z e to the minus x times with a minus sign and another minus sign times z e to the minus x. So you see that this is this you have to compute in 0, in infinity, and in 0. So in infinity, this is 0, goes to 0 exponentially. This term goes to 0 exponentially, so this is 0. And in 0, this term is 0. Okay? So this term does not contribute. And you have that this is minus kt to the 3/2 times the integral from 0 to infinity dx with 2/3 dx x to the 3 over 2 divided by 1, z to the minus 1. I divide by this e to the x minus 1. So you see, this is an integral which now looks very similar to the integral. Sorry? Here? This is the integral of this, right?
We are using integration by parts, right?
Yeah. So this you integrate and this you differentiate. Okay? So the integral of this, so here you take x dx is the differential of 2/3 x to the 3/2. And log of this is dx times this. Is the integral of dx. Right? Okay, so you see this is nice because it's an integral which is of the same form of the integral which you get, for example, when you compute the number of particles. Only that here you would get, instead of x to the 3/2, you would get x to the 1/2 if you make this change of variable. Okay. So and also you see that here you get kt to the 3/2 from the change of variable. And with this 2m to the 3/2, essentially you get something which is proportional to the 1 over lambda cube, okay, which is this thermal wavelength. So if you do the calculation properly, let me just write down the result. What you can write is that PV over KT is, you can write it as 1 over lambda cube times the function, which I'm going to define, of the chemical potential. And likewise, this n can be written as 1 over lambda cube times the same function of 1/2 in 3/2 of the chemical potential, where this function and then there are the part here there is a part so there is a V here, there is a V here, minus there is the part which depends on the energy on the zero energy level. Okay. Where this function g in general nu of z is defined as 1 over the gamma of z, the gamma of nu. Nu is either 5/2 or 3/2, or in general can be any other number. Okay. So am I missing something? Okay. So very good. So mathematically, this is the way in which I can write my problem. So the problem is that if I want to study a Bose gas with a certain number of particles in a certain volume, then what I should do is to eliminate, so solve this equation here for z as a function of n and v, and then put it here and solve for the equation of state. Now, we can go back. So we have already discussed the behavior at large temperature. So the behavior when the temperature is large will be related to the properties when the fugacity is small. So let me, in order to see this, let us compute the behavior of this function for z small. So for small z, this g nu of z, you can write it as 1 over gamma of nu. And then you can put a z here, and you will have dx x to the nu minus 1. And you can write it in this form. Okay. What I've done is just to multiply below, above and below by z e to the minus x. Okay. Now, if z is small, what I can do is to expand 1 over 1 minus z e to the minus x as a series of geometric series. So I have a sum from n from 0 to infinity of the integral from 0 to infinity in dx x to the nu minus 1. And then I have e to the minus x, I have z to the n, and e to the minus n plus 1 times x. Okay. Now if I do another change of variables, which is I call, say, y is equal to n plus 1 times x. So this integral here becomes the gamma of nu times divided by n plus 1 to the nu. Okay, because yes, if you do this change of variable, x is y divided by n plus 1. So you have n plus 1 over n plus 1 to the nu, which comes from here. And the integral which you have in y is just the gamma function. Okay. So you see the expansion for small z of this is rather simple. So the gamma function cancels from here and here. Then you have this is z sum from n equal to 0 to infinity of z to the n over n plus 1 to the nu. Okay? Actually, this is for z equal, which is between 0 and 1, this is exact. Okay. So, by the way, it is clear from what we have said so far that z, which is e to the beta mu, must be less than 1. Because otherwise this integral does not converge. Okay? So this means that the chemical potential has to be negative. In general, in a Bose system, the chemical potential has to be smaller than the smallest energy level. Because otherwise, the number of particles in that energy level at the divergence become negative. Okay? And of course, since z is like this, so z is between 0 and 1. And you see that so the series converges when z is in the integral 0, 1. So this is say alternative definition of this function. In particular, notice that G nu computed in 1 is this series which is as a function of nu. This is called the Riemann Zeta-Function. Okay, and there are some number which one can compute. So you see, for example, the high temperature so at high temperatures, we expect that Z will be very small. And for Z, which is very small, you can approximate G nu as essentially Z times 1 plus Z over 2 to the nu plus higher order things. So you see that well, if you forget about these two terms, which you can forget in this limit, then this you get the usual result that to lead in order PV So P, from this you get that P over KT is equal to Z over lambda 3 times 1 plus Z over 2 to the 5 over 2, which is 4 square root 2. And from this you get that N over V is equal to Z over lambda 3, 1 plus 1 plus Z over 2 square root 2 plus higher order terms. So from this you see that Z lambda 3 times N over V is Z1 plus Z2 over square root 2. So when this object is small, then Z is small, and so this expansion is is a good approximation. And so when this is small, what you can do is well, essentially invert this relation and compute Z as a function of this object and essentially compute the virial expansion. Okay, so you can study the limit when n lambda cube is very, very small by just inverting this relation, which tells you that to leading order Z is equal to n lambda cube. Okay. Now, if you use this equation you can write it as Z is of order n lambda cube divided by 1 plus Z over 2 square root 2, which is here to leading order you can expand this for small z and substitute that Z is equal to this in order to compute the next to leading order. Okay, so this is n lambda cube, which was by 1 minus n lambda cube to the 2 square root 2 plus higher order terms in n lambda cube. Okay, and now what you can do is you substitute this into this expression, and you would get the virial expansion in the form, say, n over v times 1 plus a1 times n lambda cube plus etc. etc. Okay. So and you can compute this first virial coefficient a1 is if you do this calculation properly, you will get that this is minus 1 over square root 4 pi. Okay, and likewise you can compute all the other terms. Okay, but we are not very much interested in high temperature and low pressure. We are interested in understanding what happens at low temperatures. Okay, because that is because essentially what this is telling you is that essentially this will behave more or less as an ideal classical gas. Okay, and well, one interesting thing which we can do as an exercise is to compute the specific heat. So the specific heat at high temperature, in this case, will be equal to 3/2 1 plus 1/8 square root 2 times n lambda cube plus higher order terms. So the important thing of this is that this term is positive. So what this is telling you is that with respect to, as a function of temperature, the specific heat, if this is the specific heat of the classical ideal gas, which is equal to 3/2, then the Bose gas will have a specific heat which is slightly larger than this, and actually it will be increasing because you can see that Z is a decreasing function of T. So as T decreases, Z will increase. But so this is the high T behavior of the specific heat. But we know that at small temperature, the specific heat must go to 0 somehow. Okay. So this means that there must be a maximum somewhere here. Okay. So there must be sort of maximum, and we are going to see that this maximum actually is a cusp. Will occur with a cusp. Okay. Okay, so let's focus on the low temperature regime. Now, if we focus on the low temperature regime, then we focus on the case where Z is close to 1. Now, when Z is close to 1, so one important thing also you can realize that this function here is an increasing function of Z. Okay, so if you do the derivative of this function with respect to Z, this is 1 over the gamma of nu, and then you have the integral of this term here. So you get, say, Z to the minus 1 e to the x minus 1 squared, and then you get, and there is a minus sign, and then you have the derivative of this, which is minus Z 1 over Z squared times e to the x, right? Now this is clearly 1 over gamma of nu times integral 0 infinity dx x to the nu minus 1 e to the x minus z squared times e to the x. So it is clear that this is a positive thing, and this is positive. Okay. So all these functions here are increasing function of z. So as you decrease temperature, z will increase, and at a certain point, z will become heat the value 1. Okay, and at this value 1, so the number of particles, you see the number of particles which are in energy state which are larger than with energy larger than 0 is bounded above. Okay, so the number of particles in energy levels larger than epsilon, which is V over lambda, or positive energy levels. So this is less or equal to V over lambda 3 times this function computed in 1, which is the Riemann Zeta-Function of 3/2. Okay? So what happens is when you decrease the temperature, so as long as the total number of particles is larger than this, so as long as n is larger than v lambda to the 3 times c to the 3/2, then all the particles can be accommodated in the positive energy eigenstates. Okay? But at, you see, when the temperature decreases, so this condition again can be expressed in the form n lambda 3 sorry, as long as the number of particles is less than this, no? Then you can put all the particles in. So again, this condition is can be expressed as n lambda 3 being less than z to the 3/2. And you see this. This is a condition which will be violated when the temperature decreases, because this is going as T to the minus 3/2. Okay? So as the temperature decreases, lambda increases. So, and there will be a particular temperature, T, when the number of particles, the total number of particles will be equal to the maximum number of particles which you can put in positive energy levels. Okay? So what happened at this point is that Z will be very close to 1. And essentially, this term will become very large. Okay, so this term is the number of particles which are in the state with 0 energy. Okay, so you will have that a finite fraction of the particles. You will start having a number of particles in this at 0 energy state, which is macroscopic. You have a macroscopic occupation of the 0 energy state, and this is called Bose-Einstein condensation. So this phenomenon is called Bose-Einstein condensation. So let us see what happens in Bose-Einstein condensation. So in Bose-Einstein condensation, you will have that your system is decomposed in two components, in two phases. So one phase is so the temperature T, the critical temperature at which this Bose-Einstein condensation occurs, can be deduced from this equation here. So is given by h squared over 2 pi m k times n over v times the zeta function of 3/2 to the 2/3. It's just inverting the relation which I told you about. You see, this is precisely if you take this here and this here, this is precisely the critical the wavelength, thermal wavelength squared. And so this is precisely the equation before. So if we are at temperature T less than Tc, then the number of particles will be split into a number of particles in the positive energy levels plus a number of particles in the zero energy level. So this so you'll have say a normal phase which is composed of the particles which occupy positive energy states. And so the number of these particles will be equal to this equation with z equal to 0. So it will be V over lambda 3 times the z of 3 half. And then these other particles here will be exactly n minus this. Okay. And this is a condensed phase of n0, which is n minus is n particles. Okay, so this condensed phase is a bit like, if you want, is a phenomenon which is similar to a condensation of a gas phase into a liquid phase, because there is a very dramatic reduction, a strong reduction in the specific volume. But here the condensation does not occur in real space, but it occurs in momentum space, because there is there is a finite fraction of particles which condensate into one state of with wavelength with k equal to 0. Okay. Now, so if you follow, so if you plot the fraction of particles in the condensed phase as a function of temperature, this will be 0 up to a certain temperature Tc, and then will go up to 1. At temperature equal to 0, all the particles will be in the zero energy state. And likewise, the number of particles in the positive energy states will be essentially, the fraction will be equal to 1, and then they will go down. Okay. Now this property is this feature is responsible for very anomalous properties of the Bose gas in the condensed phase. So let us discuss this. So, for example, you see that the pressure at T less than Tc will just be a function of the temperature. So the pressure will be equal to kT over lambda 3 times zeta function of 5 over 2, which is a number. Okay, so it's a function of the temperature, does not depend on the volume. So this means that the derivative, so the derivative of the pressure on the volume is equal to 0. So this is a gas which has infinite compressibility. So the kT, which is 1 over minus 1 over V dV dP at constant T, is equal to 0, is infinite. Okay? So it is infinite compressibility. Because essentially, because essentially, I mean, the physical reason is that you can put as many particles as you want in the zero energy state. Okay, so if you add particles to the system at this temperature, all the particles that at a fixed if the volume is fixed and the temperature is fixed, you can add particles to the system and they will go to the zero energy state, and you can add as many particles as you want. And indeed the chemical potential is zero, so the energy to add particles is strictly zero. So the chemical potential is zero because Z is equal to 1. So, and you also see by this that the fluctuation in the number of particles will be very large. So the fluctuations, you remember we showed that the fluctuations in the number of particles is related, in the grand canonical ensemble, is related to the compressibility. So if the compressibility is infinite, then fluctuations will also be infinite. Okay, so now, of course, so if you plot, for example, the pressure, you see the pressure will be proportional to the temperature to the 5/2. So we'll have, which is very different from that of an ideal gas, which is linear. Okay, so the pressure of an ideal gas, of an ideal Bose gas. If this is the classical regime, which is essentially nkt divided by V, then there will be a certain temperature Tc, and the pressure of the ideal gas will be essentially, ideal Bose gas will be lower than this, and then it will go to zero with this behavior. Okay. Likewise, you can compute the specific heat. So the specific heat also requires so if you want to compute the specific heat at constant volume, so this is 1/nk du dt at constant nV. Now the energy of this gas, as we have seen, is 2/3 of PV. So the energy is 2/3 of PV. So and PV is equal to this. So you see the pressure is proportional to T to the 5/3. So the derivative of the energy, so the energy also will be proportional to T to the 5/2. So the specific heat will be proportional to T to the 3/2. Okay. So if you plot the specific heat as a function of temperature, you have got CV over nk. And with the classical value, which is 3/2. As we've seen for temperature larger than Tc, the specific heat of the Bose gas will be larger than the classical specific heat. And at the temperature Tc, you will hit temperature, Z will become equal to 1, and then you will have a decreasing trend. So this, so the fact that, so physically, the reason why the specific heat decreases here is because the number of particles which can, which are the number of active degrees of freedom which can transfer energy are only those which occupy positive energy states. All those particles which are in the state of zero energy do not contribute to the specific heat because they cannot transfer energy. Okay? So the reduction of the specific heat is not because of a thermal problem, but because the number of particles changes. So it's exactly related to this feature here. Okay? Indeed, you see this behavior here is the same behavior as the fraction of particles in the positive energy state. Also, this goes as T to the 3/2. Okay, by I removed it, but n is proportional to lambda to the -3. Okay, so. Okay, so you see this quantum ideal gas is quite both gases, low temperature properties which are very, very different from those of classical gas. In particular, you have this phenomenon of Bose-Einstein condensation. I would like to finish mentioning one particular system which can be described by Bose-Einstein statistics, which is which are photons. Okay. So the system I want to consider is a cavity of volume V, temperature T, and I'm considering the properties of the electromagnetic field in equilibrium at temperature T inside this cavity. Okay. Now this is a very particular system, and you can model it in different ways. In particular, you can think that well, there will be several frequencies here, and for each frequency, you can think you have an harmonic oscillator. So you can think of this as a system of harmonic oscillators. Okay, and if you think like this, so the energies of the particular harmonic oscillator with a frequency omega will be equal to n plus 1/2 h bar omega. And you can do the statistical mechanics as we have done in the canonical ensemble, considering this n. And of course, you will have, so for any, so the eigenstate will correspond to the plane waves. So for any frequency omega, you will have, so this is a system of distinguishable harmonic oscillator with different frequencies. Okay. Now, however, there is another way you can think about this by saying that these are energy levels. So So you have energy levels of energy h bar omega, and there are n particles which occupy this energy level. And you call these particles photons. And then in this framework, you discuss the system as a system as an ideal gas of Bose particles. So, but there are two things which are special to this system. So the first thing is that particles are relativistic. They are not. So the energy. So the relation between the dispersion relation will be different. And the second thing is that the number of particles is not fixed. It's not fixed at all. Okay, and this will correspond to the fact, if you think about it, that if the number of particles is not fixed, then when you do the calculation, say of the entropy, or you don't need to put a constraint on n, which means that you don't need to introduce this term which was proportional to alpha, okay, which was essentially beta mu. So it means that alpha is equal to 0 or mu is equal to 0. So for this system, mu is exactly equal to 0. Okay. So then essentially you can discuss all the properties. So the in particular so again the number the first thing you have to do is to compute the energy density. So if you want to know in a given frequency range how many modes, how many oscillators you have, okay, or how many different energy levels you have. Then the argument is always the usual one, that the number of frequencies with wave vector less than a certain k is equal to v times 2 pi cube times k to the cube, but this is wave vector, and there is the integral over the solid angle. And in addition, there is a factor 2 here, which comes from the fact that for each frequency there are two polarizations. Okay, so this is the degeneracy of 2. Okay, so if you now, the other special thing is that the frequency is the relation between the frequency and wave vector is not quadratic, but is linear. So the relation between the energy and the momentum is not quadratic, but is linear. So this is because these particles move at a speed which is speed of light. So they are relativistic objects. Okay. So this changes the fact that the energy, so the density of so the density of energy levels between with frequency between omega and omega plus d omega. So this in the unit per unit volume will be equal to essentially omega squared d omega over pi squared c cube. Okay, so you should contrast this with remember the number of energies per unit volume between energy E and E plus dE. Before it was proportional to epsilon to the 1/2. Okay, so now this is omega squared because of this different scaling, because of the different dispersion relation. Okay. Now these are the two differences, but essentially you can do all the calculation in the same, exactly in the same way. So here you, of course, you can think you have an occupation of the zero energy state, but since the number of particles is not fixed, we don't care about this altogether. So there is no, and mu will be equal to 0. So for example, the average number of particles in a state of frequency omega will be equal to 1 over e to the beta h bar omega minus 1. And the average energy with frequency omega will be equal to this time h bar omega. Okay? And so it will be equal to h bar omega e to the beta h bar omega minus 1. So that if you want to compute the total energy, the total number of photons, you have to integrate these over these over all the energies. Okay, and if you want to compute the total energy, you have to integrate. So the total energy U will be equal to h bar 1 over pi square c cube times the integral from 0 to infinity d omega h bar omega cube divided by e to the beta h bar omega minus 1. Okay. Now, so there are special. So this is per unit volume. So there is a volume here. Okay. So there are. So in particular, yes, you can do this integral now because you see this is you can change variable using x, which is beta h bar omega, and so what you see, you get a factor 1 over beta to the 4 here. So you have that the energy will be proportional to volume time temperature to the 4. Okay, and in particular, if you do the calculation, you get that this is kT to the 4 times V divided by pi squared c cube and h bar cube, which comes from the change of variable, and then you have this integral, the integral in dx of x to the 3 with e to the x minus 1, which is the zeta of 4. And zeta of 4 is well, it's gamma of 4 times zeta of 4. So this is this is a number which is pi squared over 15. It can be computed. Okay. Okay. So sorry, pi to the 4th. So you have pi squared over 15 h bar cube. So the important thing is that the energy is proportional to T to the 4 times the volume. And this is related to the fact that, so if you now ask yourself what is the radiation, how much energy is radiated from this black body, and so the radiation will be proportional to the energy density times the velocity at which these photons go out, and so the radiation is proportional to T to the 4th, the temperature to the 4th power. And this is known as Stefan-Boltzmann law. Now, likewise, you can compute you can do all the thermodynamics of this system, and so in particular, you can compute the grand canonical partition function. And when you compute the grand canonical partition function, you essentially encounter the same type of integral which you have here. Again, you have an integral which you have to do by parts, exactly the same steps. So the only different with what we have done previously is that now the density of state is different. So instead of having these 2/3, you have 1/3. Okay, and this means that the relation between so the relation between the energy and the MPV will not be equal to that PV is equal to 2/3 of the energy, but it's is 1/3. Okay. Okay. Likewise, well, the other. So you can compute from this. You can compute the entropy. So the entropy. So the Helmholtz free energy, which is the energy minus T times the entropy. So in this case, if you use the fact that Ts minus U plus nu n is equal to PV, which is the usual relation which we have used several times, which comes from the extensivity of the entropy. You see that the Helmholtz free energy is exactly equal to, since mu is equal to 0, then for these systems, the Helmholtz free energy is minus PV, which means that the entropy is going to be PV plus U divided by T. So it's 4/3 U divided by T, because PV is 1/3 of U. So if the energy goes as T to the 4, the entropy will go as T to the 3, T to the cube. Okay. Now so the other thing which you can compute is the number of photons. So the number of photons which are in your system will be computed by integrating over the density of states, density of frequencies, doing this integral, e to the beta h bar omega minus 1. And so you can see that the entropy, the number of particles will also be proportional to temperature to the cube. So it will be proportional to volume times temperature to the cube. So now however, you see that even in this case, the pressure is so if you look at this expression, so the pressure is only a function of the temperature. Does not depend on the volume. Okay, so this is again a system with infinite compressibility in the sense that the fluctuation in the number of particles is infinite. So the number of particles is not fixed, so the fluctuation in the number of particles is infinite. Okay? And the other consequence of this is that essentially the specific heat, you can compute the specific heat at constant volume. And from this you find that if you take the derivative of this, you get the specific heat would go down as t to the minus, t to the 3, okay, t cube. But if you compute the specific heat at constant pressure, it is not well defined because pressure will be is proportional is a function of temperature. You cannot change the temperature without changing the pressure, and so you can say it is infinite, or you can say that. So the last thing we can compute is what are the law of adiabatic transformation in this system. So you see, so the if you are in the PV phase diagram, this means that isothermal transformation are just flat lines, okay? Because essentially, as long as the temperature is what is fixing the pressure, not the volume. And this is related to the fact that the number of particles is not fixed. Okay, so as you increase the volume, then there will be just more photons in your system. Okay. And whereas so this is isothermal. For adiabatic transformation, we have to take S equal to constant. So S equal constant means that V times T cube must be a constant. And since the pressure is proportional to the temperature to the fourth, then you see this is PV to the 4/3 equal constant. These are adiabatic. And you see this is different from what you get in a classical gas where there is 5/3. Okay, so adiabatic will be PV to the 4/3 constant. Okay, so so the gas of photons have very particular thermodynamics, both because they of the quantum statistics and because of the fact that it is a system at zero chemical potential. It is a system of relativistic particles. Okay. Okay, so we see on Friday. For the last lecture, we will discuss Fermi systems. What happens in Fermi systems.